Hello everyone, today we will start the introduction about the rigid pavement design. We will use 2 lectures to finish all the contents in this topic. First, let's have a brief review about the rigid pavement. In the rigid pavement, the PCC slab is placed on top of the subgrade layer. Sometimes we will insert the base or subbase layers in between. The PCC slabs are connected with the transverse and longitudinal joints, and depending on the types of the joints, we can identify the types of the rigid pavements. In the rigid pavement design, we are especially interested in estimating the thickness of the PCC slabs. In this class, we will only introduce the AASHTO method for the design of the rigid pavements. Similar to the flexible pavement, in the design of the rigid pavements, we have to consider the pavement performance, the impact of the traffic loadings, the roadbed or the subgrade soil properties, the environmental impact, the reliability of the pavement structure, life cycle cost, and the shallow design of the pavement. The AASHTO method can be applied for different types of the rigid pavements, including the joint plant concrete pavement, joint reinforcement concrete pavement, and continuous reinforcement concrete pavement. The procedure of the rigid pavement design with the AASHTO method is very similar to the one applied for the flexible pavement. Usually in the design of the rigid pavement, the most important component we have to estimate is the slab thickness, which will also determine the pavement strength to support the traffic loadings. In the rigid pavement design, it's very important for us to estimate the traffic loadings, which is usually measured as ESALs. And in this page, there's one equation for us to estimate the ESAL. This one is very similar to the one we provided for the flexible pavement, but the coefficients are different. Also, there are some new parameters applied for the estimation. Generally, the value of ESAL is a function of the standard normal deviate ZR, the overall standard deviation S0, the thickness of the PCC slab, which is a capital D, the changes in serviceability, delta PSI, terminal serviceability PT, modulus of rupture, drainage coefficient CD, load transfer coefficient, modulus of elasticity, and modulus of subgrade reaction. Here you can see that there are 3 additional variables we have to introduce for the estimation of the traffic load applied for the rigid pavement. That is modulus of rupture, load transfer coefficient, and modulus of subgrade reaction. We will introduce more details about these 3 variables in the future lectures. For the analysis of the rigid pavement, we have to recall the stress analysis of the rigid pavements in the previous lectures. In that analysis, we assume that the PCC slabs are linearly elastic and linearly thermoelastic. Also, for the unbound layers, including the base and the subgrade layers, we assume that they are linearly elastic and they act as Winkler spring. This is actually the most significant difference between the flexible pavement and rigid pavement. Actually, for the rigid pavement, we have to use the modulus of the subgrade reaction for the design instead of the modulus of resilience. In the design of the rigid pavement, we have to use the modulus of the subgrade reaction, which will measure the relationship between the deflection of the subgrade layers and the load applied to the PCC slab. Actually, the value of K depends on the moisture contents and the density of the subgrade soil. The value of K can be estimated if we are provided with CBR or MR values, and then we can record the relationship between K and CBR or MR to find out the K values. Also, if we introduce the subbase between the PCC slab and the subgrade layers, we need to use the composite K to find out the weighted modulus of the subgrade reaction as the designed K value. In addition, similar to the flexible pavement, the value of the subgrade reaction K varies over the seasons. So we have to take account of the seasonal variation to find out the effective K for the design of the flexible pavement. The table here shows some typical K values for different soil types. For the fine-grained soil, the typical K values varies from 20 to 34 megapascal per meter, and this will be equivalent to the value of CBR around 2.5 to 3.5. For the sand and sand gravel mixture, the typical K values is between 35 to 49, which is equivalent to the CBR of 4.5 to 7.5. For the sand and sand gravel mixture relative free of plastic fines, then the K value varies around 50 to 60, and the CBR is between 8.5 and 12. In the estimation of the ESAL for the flexible pavement, we have to know the elastic modulus of the concrete slab, EC. Actually, in the AASHTO method, we assume that EC is a function of the compressive strength, which can be measured by a universal testing machine. The three equations here shows the relationship between EC and the compressive strength. If the compressive strength is in the unit of gigapascal, then we have EC equal to 4730 times square root of FC prime. FC prime is the compressive strength. If FC is in PSI, we will have EC equal to 57,000 times the square root of FC prime. Also, if FC is in megapascal, we can let EC equal to 0.043 times rho to the power of 1.5 times the square root of FC prime. Here EC is in the unit of gigapascal, and the rho is the unit weight, which is the density of the concrete slab. Usually it's set as 2320 kilonewton per meter cube. In the estimation, one important variable we have to introduce is the modulus of rupture, which is also called the flexure strength, capital SC. It's also a function of the compressive strength, FC. If FC is in the unit of megapascal, we have SC equal to 0.553 times the square root of FC. If FC is in PSI, we have SC equal to 8 to 10 times the square root of FC. Usually, for the field design, we will assume that the ratio between SC and FC is between 0.11 and 0.23. We will find some typical values in this range for the design of the rigid pavement. The figure here shows the relationship between the modulus of rupture and the compressive strength. The points in this figure comes from the result from the experiment, and you can actually apply various models to calibrate the relationship between the modulus of rupture and the compressive strength. Basically, with a higher compressive strength, the modulus of the rupture will be larger. We can also apply the AI procedure for the estimation of the ESAL based on the average daily traffic and the truck traffic. Basically, the value of ESAL will be a function of the average daily traffic, ADT, the percentage of the trucks, T, the truck factor, the total gross factor, and the directional distribution factor and the length distribution factor. Also, for the total gross factor is a function of the annual traffic growth rate and the design period of the rigid pavement. Similar to the flexible pavement, we also need to define the load equivalency factor LEF to identify the damage of the chalk applied to the rigid pavement. The table here compares the load equivalency factor applied for the flexible and rigid pavement, and the values are categorized for the axial types, including single, tandem, and trident axials, and the spacing types, including zero spacing, which would be the single axial only, typical spacing, and large spacing. Basically, by comparing the flexible and the rigid pavements, we can see that their EFs applied for the rigid pavement is usually larger than that for the flexible pavement. The table here provides more typical load equivalency factors for the flexible and rigid pavements with different axial load for single and tandem axials. For the flexible pavement, the terminal serviceability is defined as 2.5 and the pavement structural number is set as 3.0. For the rigid pavement, the thickness is set as 9 inches. Basically, when you find the load is higher than the standard axial load, 80 kN, you will observe that the load equivalence factor for the rigid pavement will be higher than those applied for the flexible pavement. This table shows the load equivalency factor applied for the flexible pavement with the thickness of 9 inches and the terminal serviceability of 2.5. In this table, you can find out the LEFs applied for different axial loads and different axial types, including single, tandem, and trident axials. The table here shows some typical chalk factors applied for different vehicle classes defined by FHWA. Basically, for motorcycles and passenger cars, the chalk factors are all set as 0. And for the other types of the vehicles, including buses and heavy-duty trucks, the chalk factors are all positive. If you make a comparison between the rigid and the flexible pavement, you can see that the chalk factors applied for these two designs are the same. Now let's make a quick summary about the traffic analysis for the rigid and the flexible pavement design. Basically, the procedure of the traffic loading estimation are the same for the flexible and the rigid pavements. However, the rigid ESALs is not the same to the flexible ESALs. The difference comes from the response of the pavement to the traffic loads, which means that the load equivalence factor for the rigid pavement is different from the LEF applied for the flexible pavement. The equation here shows the estimation of the LEF applied for the rigid pavement, and this equation is almost the same to the flexible pavement. However, the coefficients in the equation are different. In this equation, the definitions of the variables are the same to the flexible pavement. We have NTX as the number of x-axial load applications, NT18 as the number of 80 kN or 18 kpounds single axial load applications, LX as the load in kilopounds on one single axial or one set of tandem axial or one set of trident axial. L2 is defined as the axial code, 1 for single axial, 2 for tandem axial, and 3 for trident axial. In the equation, we have a new variable d as the thickness of the slab. The unit is set as inches. And this one is only applied for the PCC slab and the rigid pavement design. PT is set as the terminal serviceability, and GT is set as a variable as the function of PT. In the AASHTO method, the design criteria should also be specified. Actually, in the rigid pavement design, we have to consider two primary criteria. The first one is the fatigue of concrete slab, which is only applied for the pavement structure. where we have to consider the cracking or functional failure of the PCC slab. The second one is the erosion of the subgrade soil, and this one is only applied for the subbase or subgrade layers. We need to investigate the factor of mud pumping or joint faulting for the rigid pavement structure. In the rigid pavement, the fatigue cracking is usually caused by the mid-slab loading, which is away from the transverse joint. And this can create the critical edge stresses, and the tensile cracking will then be generated at the bottom of the concrete slab, which is also called the fatigue cracking. While for the erosion, it's usually caused by the corner loading, where it will produce the critical pavement deflection at the PCC slab, and this kind of deflection will result in the mud pumping effect to the rigid pavement. Now let's introduce a model to describe the erosion criteria applied for the rigid pavement design. Actually, there are some necessary conditions for the generation of mud pumping, which is related to the erosion criteria. First, for the subgrade soil, they should go into suspension, and there are some erodibility for the subbase or the subgrade soils. And second, there should be some free waters between the slab and the subgrade layers. In addition, we should observe some frequent heavy wear loads applied to the PCC slab. With that, we will observe the large deflections to those slabs. However, currently, there isn't any mechanistic model applied to describe the mud pumping effect. In that sense, we have to introduce an empirical model to identify the erosion criteria. For the model development, we have to consider some critical factors, including subbase and subgrade soil characteristics, the drainage conditions, and the joint load transfer effectiveness, which will define how the load is transferred to the subgrade soil. In the rigid pavement design, there are some approaches applied based on different assumptions. First, let's introduce one erosion model applied for the joint plane concrete pavement, and this model is used to estimate the pumping index PI. Actually, the pumping index is the value in the scale of 0 to 3. 0 indicates no pumping, 1 indicates low severity pumping, 2 for medium, and 3 for high. The equation here shows the estimation of the pumping index as a function of the traffic load, N18 as the ESAL, H as the slab thickness, S as the soil type, and P as the annual precipitation. Fi is the freezing index, which is the degree days. In the equation, the soil type is actually defined based on the AASHTO soil classification, and S is set as 0 for the coarse grain soil, which is the type of A1 to A3, and it's 1 for the fine grain soil, which is the type of A4 to A7. For the freezing index, is defined as the degree days, which is the total degree days below 32 degrees. That is the summation of 32 minus T, which would be the temperature in Fahrenheit, times the number of days. For the joint reinforced concrete pavement, the erosion model is a little bit different. In this model, the pumping index is also a function of the variable D. Here, D is an indicator for the presence of the drainage system, and D is 0 if there isn't any sub-drainage system, and it's 1 if there isn't a sub-drainage system. Also, you have to pay attention to the variable D. In our previous slides, we showed that D as the slab thickness. Here, in this specific equation, we use D as the indicator for the presence of the drainage systems. Similar to the flexible pavement design, we also need to consider the drainage coefficient CD for the rigid pavement design, and this one is applied to define the drainage characteristics of the subgrade, and is related to the amount of the water that the subgrade can retain. Usually for the sandy materials, the drainage coefficient is set as 1.0. The table here shows some recommended values of the drainage coefficients applied for the rigid pavement. And these values are categorized based on the quality of the drainage system and the percentage of the time that the pavement structure is exposed to the moisture level approaching saturation. For the quality of the drainage is categorized into 5 types: excellent, good, fair, poor, and very poor. And for the percentage of the time, we have less than 1%, 1 to 5%, 5 to 25%, and higher than 25%. For each cell, there is a bound range of the drainage coefficient, and we have to choose an appropriate value in that range for the design of the rigid pavement. In Ontario, MTO also recommended some typical drainage coefficient values for the rigid pavements, and the recommendations is based on the quality of the drainage system and the climate conditions. For the quality is categorized as excellent, good, fair, poor, and very poor, and the definition is the same to FHWA. For the climate condition is categorized as dry and wet. The dry condition is defined as the precipitation less than or equal to 508 mm per year. And the wet condition is set as the precipitation is higher than 508 mm per year. In the rigid pavement design, we also need to identify the load transfer efficiency at the joints for us to estimate the load transferred from the PCC slab to the subgrade layers. If there isn't any subbase layer and there isn't any dowel bars, then none of the load will be transferred from one PCC slab to the other one. So the load transfer efficiency is set as 0%. And if there's a subbase layer behind the PCC slab, we can use the aggregate interlocking effect to transfer the load from one PCC slab to the other one. However, in this case, the load transfer efficiency will not be 100%. If we have the dowel bar to connect two PCC slabs, then all the load will be transferred from one slab to the other one. So we have the load transfer efficiency as 100%. Generally, the load transfer coefficient is a factor applied to account for the ability of the pavement to transfer across discontinuities such as the slab joints or the cracks. Also, this coefficient is applied for the pavement with the dowel bars at the joints, tight shoulders, and some other situations. And the coefficient is not constant. Actually, it's related to the traffic loadings. The coefficient will be higher with increased traffic for a given set of the conditions. Moreover, if dowels are used for the PCC slabs, then the size and the spacing must be determined by the local agency procedures. Usually the dowel diameter is set as 1/8 of the slab thickness, and the spacing is set as 12 inches and the length is 18 inches. The table here shows some recommended load transfer coefficients for various pavement types and design conditions. And actually, it gives us the typical values for the pavement with different shoulders, including the asphalt shoulder and tied PCC shoulder. And the different load transfer devices. We can identify the load transfer coefficient for the joined plain concrete pavement and joint reinforced concrete pavement, and the continuous reinforced concrete pavement. Usually, the higher transfer efficiency indicates a smaller value of the transfer coefficient. And in the design, we want to have higher load transfer efficiency, which means smaller value of capital J. We know that the load transfer coefficient is related to the aggregate interlocking effect occurred at the subbase layer of the rigid pavement. And this effect will be observed at the PCC joint or the cracking of the pavement. So the effect of the aggregate interlocking will be determined by the width of the cracking or the joint. Usually we assume that when the cracks are wider than 0.9 millimeters, we will ignore the aggregate interlocking effect. With that, we can say that the load transfer efficiency will be 0%. With this, we have introduced most of the variables applied for the estimation of ESAL for the rigid pavement, including the modulus of rupture, drainage coefficient, load transfer coefficient, and modulus of elasticity. In the next lecture, we will introduce more details about the modulus of subgrade reaction, which is the most important variable for the design of the rigid pavement. So that's all about the lecture today. Thank you very much for your attention. In this lecture, we introduce some basic concepts in the AASHTO method for the rigid pavement design. In the next lecture, we will try to finish the rest of the contents for the design of the rigid pavement with the AASHTO method.